In Chapter 3, we'll start discussing compounds and the counting unit we use most in chemistry, the mole. There are 12 sections in Chapter 3. Sections 3.6 and 3.12 won't be covered in class, but it would be time well spent to work through the nomenclature review in 3.6 on your own. Our first task in Chapter 3 is to interpret chemical formulas and write formulas to represent compounds. We'll also learn to differentiate between atomic and molecular elements as well as molecular and ionic compounds. Let's begin. Nomenclature describes the system for naming chemical compounds given a formula. Formulas combine the symbols of the elements with subscripts indicating how many of each atom is present in one formula unit of a compound. We'll often see groups of elements enclosed in parentheses, such as in barium phosphate here. The unit, PO4, is a special grouping called a polyatomic ion, which we'll discuss further later in the chapter. For now, I want you to be able to look at a formula and tell me how many atoms are present. For example, our barium phosphate formula unit contains 3 barium atoms. If there isn't a subscript listed, we can assume it's a 1, so we have 1 times 2 equals 2 phosphorus atoms, and 4 times 2 equals 8 oxygen atoms, since we are combining 2 units of phosphate with every 3 barium atoms. Here's one for you to try. How many atoms of each element are present in one formula unit of magnesium chlorate, ammonium sulfite? Magnesium chlorate contains 1 magnesium atom, 1 times 2 equals 2 chlorine atoms, and 3 times 2 equals 6 oxygen atoms. Ammonium sulfite contains 1 times 2 equals 2 nitrogen atoms, 4 times 2 equals 8 hydrogen atoms, 1 sulfur atom, and 3 oxygen atoms. As we encounter more examples of compounds and formulas, you'll notice that we distinguish between atoms of an element, molecules, and formula units. So how do we tell the difference? Molecular compounds are those compounds made up entirely of nonmetal atoms. Because nonmetal atoms are all on the same side of the periodic table, they will share electrons in covalent bonds, which is why molecular compounds are sometimes called covalent compounds. In contrast, ionic compounds are made up of metal and nonmetal atoms. Because the metals and nonmetals are on opposite sides of the periodic table, they don't share the electrons in the same way, so we characterize their bonds as being ionic. Ionic compounds do not exist as distinct molecules, but rather as extended three-dimensional networks called lattices. For this reason, it's incorrect to refer to a formula unit of an ionic compound as a molecule, since we're talking about an extended network of metal and nonmetal atoms in a lattice and not a discrete unit. Before we can name compounds, we need to identify them as ionic or covalent compounds. Which compounds are ionic? Which compounds are covalent? Calcium chloride and iron 3 oxide are both ionic compounds since they contain metal and nonmetal atoms, while carbon tetrachloride and water are covalent or molecular compounds containing only nonmetal atoms. Some elements are never found in nature as free atoms, but rather as molecular elements. Common examples include diatomic chlorine, Cl2, phosphorus tetrahedra, P4, and sulfur rings, S8. For now, you need to be able to identify the 7 diatomic elements. We'll save the other molecular elements for advanced chemistry courses. The 7 diatomic elements include hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Except for hydrogen, they conveniently form the number 7, starting with element 7. Be sure to memorize these diatomic elements. Finally, keep in mind that we'll encounter different allotropes, or molecular forms, of elements during general chemistry. Whenever you need to select an allotrope, if it's not immediately clear, such as the case of molecular oxygen and ozone, the textbook and I will tell you which form to use. For example, we'll see carbon as diamond and carbon as graphite several times throughout general chemistry. Both forms of carbon can be indicated as a C for carbon, so we'll tell you which allotrope you're working with. As always, I'll leave you with the parting thoughts of the authors.